Hi class, today we're going to start on section 3.4, which is real zeros of polynomials. So we're first going to start with rational zeros of polynomials. All right, and so a rational zero is, or just a rational number in general, is of the form a over b, where a and b are integers. So this is a rational number. All right, and so then there are two ways to write a polynomial with their zeros. So we have a factored form, and this is when our polynomial looks like this: x minus 2 times x minus 3 times x plus 1. So in this case, we have our zeros are 2, 3, and negative 1. So this is where if you plug in that number into your polynomial, you will get 0 out. So that's what it means by the zeros. So this is our factored form. And then we have our expanded form. So here we have the same polynomial, and I've FOILed it out. You could do it with a little work. I'm just skipping the work to write it out a little cleaner. So it is x cubed minus 4x squared plus x plus 6. And now notice that here in our factored form, negative 2 times negative 3 times 1, this equals 6. And this matches, there we go, our 6 here. So that's a key observation to have. So with this key observation, we will get our rational zeros theorem. So here, this states that if the polynomial p of x equaling a n x raised to the n all the way to a1x plus a naught, if this has integer coefficients, and also with the conditions that an does not equal 0 and a naught does not equal 0, then every rational zero of p is of the form little p over q, where little p and q are integers. And two key conditions as well. One, little p is a factor of a naught. We should all remember what factors are. They are the numbers that when multiplied together will give you p, also known as the divisors of p. So if p was 6, then 3, 2, and 1, those would be divisors, and 6 as well, would be divisors of 6. And then 2, q is a factor of an. And remember, an is our leading coefficient. I'll remind us here. This is our constant coefficient. And this is our leading coefficient. Just to help y'all remember. All right. So then note, when the leading coefficient there's a t there, is 1 or negative 1, then the rational zeros, whoops, that does not look like a V, does it? Then the rational zeros must be factors of the constant term. All right, and another important note. This one's really important to remember. So this does not mean every zero. Whoops, this is not the correct sentence at all. I'm so sorry, y'all. All right, so this does not mean that every zero of a polynomial with integer coefficients is rational. It only means that if a zero is rational, then it's of this form. For example, if we were to take x squared minus 2, well, this gets factored into x minus the square root of 2, x plus the square root of 2. And plus or minus the square root of 2 is not rational. I'm not sure if your other classes have told you about this, but any square root of a prime number, those are irrational numbers. They cannot be expressed as a fraction with integers. So that's just a helpful thing to know. I'm not sure if your other class went over it, but I feel like they should have. It's not the most important thing you'll learn in pre-calc, but it's helpful to know right now. All right, so now we're going to do an example where we find the rational zeros of a polynomial. So we're going to look at the polynomial p of x equals x cubed minus 3x plus 2. So our leading coefficient, should be an O, is 1. So then any rational zero is a factor of 2. So this means that plus and minus 1 and plus and minus 2 are our factors. So let's test them. And remember that you need the positive and negative factors of a number, so they all are technically factors. So first let's try p of 1. So this is 1 cubed minus 3 of 1 plus 2. This equals 1 minus 3 plus 2, which equals 0. So yes, this one is a 0. Then we have p of negative 1. This equals negative 1 cubed minus 3 times minus 1 plus 2. And this equals minus 1 plus 3 plus 2. This equals 4, so this is not a 0. And I'm sorry if the calculations are going pretty fast. I'm hoping that they're pretty clear to see. And if you want to check them on your own, I highly encourage that as well. And then p of 2, this is 2 cubed minus 3 times 2 plus 2, which equals 8 minus 6 plus 2. This equals 4. This is also not a 0. And then p of negative 2. So we get negative 2 cubed minus 3 times negative 2 plus 2. And this is negative 8 plus 6 plus 2. Well, this does equal 0. So here we have our 2 zeros that we've checked. So therefore, 1 and -2 are zeros of our polynomial p. All right. So now we're going to have a helpful way to determine the number of zeros possible in a polynomial. So we're going to, it is called Descartes' rule of signs. And the important part here is that you know what a variation of signs is. So a variation of signs is when you have a polynomial written in decreasing order of powers, which is normally how we've been writing them, and we're omitting the zeros. So when we divide, we like to keep the zeros, but when we are doing variation of signs, we omit them. And then the variation in sign occurs when coefficients next to each other have opposite signs. So I'm going to illustrate this with an example. So we have x to the 6th minus 3x to the 5th plus 4x squared plus 30, oh wait, I want a minus there, whoops, minus 37x minus 6. And notice we've omitted x cubed. There's no, we're just, since it has a 0 coefficient, we're just omitting it. So here we have a variation of sign here. We have a variation of sign here. So you see, we have a positive 1, there's a secret +1 here, going to a negative. So we have a positive and then a negative. Oh, oops, there's also 1 here. And then we have a negative to a positive. And then we have a positive to a negative. And then here, since we have a negative to a negative, this is not a variation of sign. So we only care about these 3 red ones. So there are 3 sign variations. All right, so now we are actually going to tell you what Descartes' rule of sign is. All right, so Descartes' rule of signs. So we're gonna let P be a polynomial with real coefficients. Then 1, the number of positive real zeros, they're either equal to the number of variations or less than by an even whole number. It was equal to the number So in our former example, it would be 3 or it would be 1. Those are our possible options. So it's equal to 3 in sign, or is less than this by an even number. Okay, so this lets us know how many possible zeros that we will have. And then 2, the number of positive, I'm sorry, we had positive before, of negative, real zeros. All right, so what this theorem is saying is that the number of positive real coefficients is equal to the number of variations of sign less than this or by an even number. And then, oh, whoops, very important note here that I made a mistake on. The number of negative real zeros is the number of variations of sign when we do negative x instead of x. So this is the very important distinction between the two. So now we're going to do some examples to illustrate what this looks like. All right, so we're going to determine the number of positive and negative zeros of this polynomial. P of x equals 3x to the 6th minus 5x to the 5th minus 3x squared plus 4x plus 6. So first we're going to look at the positive since it's already written here. So we have a variation in sign here, and then we have a variation in sign here. So we have two variations of sign. So there is either 2 or 0 positive zeros. All right, and now we're going to look at P of negative x. So this is 3 of negative x to the 6th minus 5 negative x to the 5th minus 3 negative x squared plus 4 negative x plus 6. So now we're going to rewrite it. And remember, when you have a negative number to an even power, that becomes positive. And when you have a negative number to an odd power, that stays negative. So here we just get 3x to the 6th, and then this stays negative, and we're going to have that negative x cancel with the negative 5, so then we get a plus 5x to the 5th. As negative will cancel, so we'll just get a negative 3x squared. This negative will get pulled out front, so minus 4x and then plus 6. So now we're going to look at our variations of sign. We have one here, and we have one here. So there's also 2. So 2 variations. So there is either 2 or 0. Oops, negative zeros. I always want to write positive. All right, so now this means that there are either 4, 2, or 0 total possible zeros. So here we took combinations of the 2's and the 0's. So 2 plus 2 is 4, 2 plus 0 is 2, and 0 plus 0 is 0. So that gives us our total possible. All right, thank you for your time. And next video, we will talk about complex zeros and the fundamental theorem of algebra.